Hello, everyone. Okay, so who are we and what we do? We are Tucson Embedded Systems, known as TES. We are one of the founding members of the FACE Consortium, as well as the first commercial phase verification authority. We have over 25 years of experience working on model-based systems engineering and modular open systems spanning multiple industries. Here at TES, we have developed a software development kit to facilitate the process of creating phase units of conformance. We named the SDK FC178, which stands for Airworthy Phase Compute Environment, and the number 178 comes from it being developed in accordance with DO 178. FC178 runs in our model-based development environment tool suite called Awesome. That's a catchy acronym. And we will be referencing this tool throughout the presentation. The SDK includes a TSS, iOS, HMFM configuration services, and a C++ library that consists of system calls that conform to the FACE 3.1 and 3.2 technical standard. So here we have the 5 segments described in the FACE technical standard 3.1. We will emphasize on each segment in the following slides and how FC178 can facilitate the development and integration of those segments and FACE applications. For each of the segments, we will aim at describing capabilities at a high level and mention some of the aspects in the development process that are required, optional, as well as some of the challenges that we as developers have encountered. If you pay attention here to the key in this diagram to the right, you will see the color-coded interfaces, some defined by the technical standard and others by FC178. The blue ovals represent some of the artifacts that are part of FC178. The blue ovals with the yellow star have significant portions of UOC code that is generated within Awesome.
Okay, I'm going to start by talking about everyone's favorite segment, the transport services segment. That's really where the FACE architecture gets its boundaryless information flow from. If you have information in a PSSS and you want to get it to a PCS, you got to go through the TSS, right? And if you want to get information from one TSS to another TSS, that you need to go through your TSS as well. And I think we all know the required TSS capabilities. Here I have listed type-specific distribution and configuration. Type-specific is just your specific data types, where you know the type of data you have, how many bits and bytes you're working with, that kind of thing. And of course, your configuration, which comes from your OSS, which I'll talk about that later. Where the TSS gets complicated and where its real power comes from are some of the optional capabilities, like the type abstract and especially the TPM, the Transport Protocol Module. One of the goals of a TSS is for it to be interoperable between different TSS implementations, and that's not really easy to do. And a lot of those incompatibilities are packaged in the TPM, or potential incompatibilities are packaged in your TPM. That's where your low-level transport code goes, where you develop your sockets and that kind of thing. And in order to package your type-specific data in a type abstract way, to abstract your type specific and send it over a wire, you have to think a lot about how you're developing your serialization and your marshalling. That's all injected into your TPM. So over the years, as we've developed AFC, and there should be an E on the end of this AFC. I don't know where that E went, but we've developed tools to actually build your type specific code from our awesome tool suite. So we take a USM, UOP supplied data model, and we can generate your type-specific data from that. We also have built into AFC a TPM and a type abstract as well. And all of the, not really boilerplate code, but all of the code you need to inject and initialize and stuff, that's all generated as much as possible by our awesome tool suite. And we found that to be very useful when developing FACE applications. The operating system segment is, of course, how FACE applications talk to your OS. Um, the and for the most part, your application will talk directly to an OSS, but through specific profiles. And I think we're all familiar with the security, safety base, safety extended, general purpose. One problem that we've had with developing some of our face applications is a lot of folks want safety base, but safety base is a pretty narrow set of POSIX calls. In fact, you can't use TCP. So when you're developing a TSS and you want to use the most common transport protocol there is, TCP, you can't use safety base. That's something to note that we've run into quite a bit. The OSS, in addition to your profiles, the OSS also gives you your HMFM, which is your error handling and fault management, and of course, building your configuration. What we've done here at TES is we've built our own OSS segment, and we've packaged it with an HMFM and a configuration class, so it does all your XML parsing and the file I/O required for that. We've also, one thing that I think is particularly useful is our OSS profiles are built are part of our build profile, our build system. So we have flags to our GCC compilers that say we want safety base or we want safety extended, and that's just a simple flag.
The input-output services segment. This segment provides the capability to communicate the platform-specific services segment, or the PSSS for short, with physical devices via device drivers using bus architectures and the OSS. An IOSS requires at least one of the bus architectures. Commonly, face applications require communication with at least one device, and the data logic of this communication must be done in the PSSS via the IOSS interface to and from the device. Some of the currently defined bus architectures from the technical standard include I2C, 1553, serial, analog, discrete, to name a few. After implementing one of these bus architectures, all other interfaces are optional, independent of the application. If the application requires communication with more than one device of different bus architectures, an I/O services for each bus architecture is required. How AFC 178 provides support for the IOSS? Well, it provides several I/O services for an IOSS. These services are ready to use for the respective bus architectures to send and receive information to and from the device. The AFC 178 I/O services can be integrated in a straightforward manner into a PSSS component using the provided configuration and the lifecycle management services. Another key feature is that the raw data coming from the device via the I/O service can be modeled using the awesome tool suite. Modeling the devices in this way allows for easy conversion from raw binary data to type-specific data that aligns with the phase data model and is ready to be transmitted via the TSS. The platform-specific services segment, or the PSSS. This segment contains software modules that are tied to a specific I/O service via the IOSS, as mentioned before. This connection makes its components less portable than those within the PCS. The PSSS consists of three subsegments: the device services, the common services, and the graphic services. The PSSS is required to have an application logic related to one of these mentioned subsegments, although a typical application uses more than just one of the subsegments. For instance, a common example is that you're logging from an IOSS connected device that uses the device services and the common services. Very common. After the developer has included at least one of the mentioned services in a component, the remaining aspects are optional. Something special about the PSSS. The requirements for the PSS component are extensive, but provide flexibility to developers to quote unquote get the job done. This flexibility allows for openness and component logic, but that is also what makes it less portable than the PCS. AFC 178 uses code generated from the awesome tool suite, which includes common component services and interfaces such as TS, OS, and conversions for I/O services. These boilerplate services and interfaces such as a TS, these boilerplate face artifacts can be easily integrated to a fully functional PSSS to communicate between the TSS and the IOSS. AFC 178 also provides several capabilities within the device services and common services subsegments that facilitate the developer's implementation for type-specific data flow between multiple PSSS and PCSs within a face application.
And finally, the PCS. Of course, that's our portable component segment. And it's really defined by what it can't do. The PCS is only allowed to talk to the TS or the OSS interfaces. It can't talk directly to devices. It can't talk directly to a display or anything like that. And that's what makes it portable. What we found at TES is that it's real easy when developing a PSSS is to put business logic there. That's what FACE calls your application logic. Everything that is portable. You're building a PSS, it talks to a device, and you just want to put your business logic right there because you're doing it. But really that goes against the spirit of the FACE architecture. You need to put as much as possible in your PCS so you actually have portable components. What we do at TES is, or as part of our AFC toolkit, is we build those other segments for you, the TS, the OSS, and lots of your device drivers and IO services. And we also build the infrastructure to inject that into your portable component and inject the serialization into your TPM. And then the rest is up to the developer, which we have found really helpful and a really great way to build FACE applications. And I think that's it for us.
Thank you, Jesus. Thank you very much, Scott.